Hello. Today we are going to start with Gauss Law and some very basics about Gauss Law you already know from your standard 12. So I will assume that kind of background, and we are going to do some interesting stuff today, and we are going to see that what are the validities for the Gauss Law. So the question for today's lecture is it that some some kind of forces, for example, some specific kind of forces, or you can say fields. Uh, you can say, is that some specific kind of forces or fields where Gauss law is valid? So is it that there are some kind of specific kinds of forces or fields where your Gauss law is valid? And indeed the answer comes out to be true. So I would assume assume the background that is aware about Gauss law. So I will just take a little bit of understanding there, and I will move forward. So, for example, I know that everybody knows that because about Gauss law. What does Gauss law suggest? So, for example, if there is a point charge, if there are certain kind of symmetries, for example, if there is a spherical symmetry, all these symmetries we have discussed, but today's lecture is mainly focused on is that there are only some certain kind of specific forces where your Gauss law can be bounded. And where I mean Gauss law means Gauss law in the present form, what we know. For example, if I have a charge Q, and if I want to find the flux enclosed, what I would do, I would simply make any sort of enclosure. If I make any sort of enclosure, and if I want to find what is the total charge enclosed, so it will be equals to Q only. And what is the net flux linked through this surface? The net flux linked through this surface, I can say Q, is given by summation net charge enclosed within that surface divided by epsilon. So net flux enclosed means E dot ds we have to find. Let's say this particular volume is, let's say this particular surface is S. So whatever net flux is enclosed to this surface, it gives you total charge enclosed divided by epsilon naught. Here total charge is small q. I hope it is clear. So this is how it is. This is how it is. This is your one way of expressing the thing. Another way of expressing the thing can be this entire this thing in differential form. So for example, I know my del dot E vector. My del dot E vector. हाँ बेटा बोलो.
सर वो आया ही नहीं अभी तक.
नहीं यार कोई नहीं आया, कोई बात नहीं, अपन लोग तो पढ़ते आने दो.
ठीक सर.
So del dot E vector gives you rho upon epsilon naught, and from here also you can find the value. So you know that your del dot E vector is given by rho upon epsilon naught, and what is rho? Rho I can write. See, I've already taught you that whenever it comes to point charge, how to write the density of a point charge? We write the density of point charge in terms of Dirac delta function. We write the charge density. We write the charge density of a point charge using a Dirac delta function. So these lectures I have already uploaded. Kindly visit them. So whenever you have to, because the people who have joined right now or probably are not aware of Dirac delta functions. The Dirac delta function is a function which suggests that there is a infinite contribution at one point, and then there is no contribution. So for example, whenever it comes to modeling the charge density of a point charge, point mass, we use this kind of function, which is called a Dirac delta function. And see, if I have a point charge, see, if there is a point charge, you obviously know that we cannot write the volume charge density of a point charge, because see, volume charge density means dq upon dv, or simply q over v if it is uniform. And here your volume is zero, because for a point charge you cannot have a volume. Even an infinitesimal small volume would make it non-point thing. So if you are talking of point, it should not have any dimension. Since it does not have any dimension, so you cannot define the volume charge density of a point charge. So what you would find is, and we've discussed it extensively in our lectures on Dirac delta function, that for such kind of ambiguities, what we have done, we have derived something called as Dirac delta function. And the property is that if I want to integrate this Dirac delta over the space, then it comes out to be 1. Okay, so this is how it is. Now, if I want to find what is the charge enclosed, there are two ways. One way is just simply find the net electric flux. So net electric flux due to this particular surface should be equals to Q upon epsilon naught. And let us see, is that the case or not? So for simplicity, I'm making a sphere of radius capital R. So what will happen? I know because of my point charge Q, the net flux enclosed, and if this is the surface, this surface area is given by R square sine theta d theta d phi r cap. This is how it is written. So on the surface, you can write your differential element ds as R square sine theta d theta d phi r cap. So kq upon R square, and here you can write capital R square into R square sine theta d theta d phi. And while you integrate it, you will get what? Sine theta d theta d phi would give you 4 pi, and this k would give you 1 upon 4 pi epsilon naught. So totality, you'll get q upon epsilon. So what it is giving? It is giving you net charge enclosed divided by epsilon. Is that clear? Now, if you want to find other way around, if you want to go with the differential law, so what differential law would give you? Differential law would give you rho upon epsilon naught, and rho as a function of r, you know, for point charge is q Dirac cube of r. And now you can simply integrate rho d tau over the surface S, and you will get q integral d tau r d cube r d tau, and this will be equal to q. So overall, you know that this is how your Gauss law functions. Now, yesterday I was trying to teach one thing, that what if the definition of a Coulomb's law change? So for example, now, so you already know that your Coulomb's law is an experimental law. It is an experimental law. So it has been found that in nature, whenever there are two charges, there are 2 point charges, the force between two is inversely proportional to the distance between the two. So it is a mutual central force, and you can say that it follows something called as inverse square law. It follows something called as inverse square law. And if at all it follows inverse square law, so you can expect that something called as Gauss law. See, I told you above also. Let's say what I want to suggest, that, for example, if this is my charge Q, whether I enclose in this surface, whether I enclose in this surface, whether I enclose in this surface, or whether I enclose in any arbitrary kind of surface, the enclosure would always consist of this charge Q. So if I want to write flux due to this charge Q from surface S1, S2, S3, or S4, so whether you write flux through S1, whether you write flux through S2, whether you write flux through S3, whether you write flux through S4, all of them, the answer would be Q upon epsilon. So you can understand that net flux enclosed is equals to the total charge enclosed divided by epsilon, provided these surfaces should enclose the charge, irrespective of their shapes, their radii, or anything. Is that clear? ऐसा होगा. But and this is true because your electric field is proportional to 1 upon r square. That is, if you have this kind of stuff, only then you can expect this sort of thing. For example, with all simplicity, without getting into any sort of difficulties by making some kind of solid angles and all those things, if I say all these surfaces S1, S2, S3 are spherical surfaces, then you know that flux through S1 can be written as integral E dot ds to S1. And let's say S1 has radius R. So what you will get? You will get K Q upon R1 ka square, and then you have R1 square sine theta d phi. And this R1 square gets cancelled, and overall you know that this particular integral would give you 4 pi. So 4 pi K Q. So you will get answer Q upon epsilon. Whether you find surface flux through S2, you will again get the answer as E dot ds, and all those things, you know that this will also come as Q upon epsilon. And this is what is your Gauss law. Gauss law suggests that the net flux enclosed through a surface S, net flux linked through surface S is equal to net charge enclosed within that surface, Gaussian surface, divided by epsilon. So this is the present form of your Gauss law. This is the present form, or what Gauss law you know. So Gauss law one knows. Okay, so this is the Gauss law that I know. Okay, that you know. Okay, and similar such constructions can be done for gravitational forces also. Now, question arises whether this kind of definition still exist for let's say any such force which may probably do not follow 1 upon r square. So, for example, just for instance, I'm giving you an example. For example, if I give you a force which, if I give you a field which varies sort of Yukawa kind of thing. So Yukawa kind of, what should I write? I will write, for example, instead if I give you this, so instead if I give you this sort of, okay, this sort of things. For example, if I write, okay, if I give you this kind of things. For example, if I write that my force now behaves as if it is, so now if my field behaves as if it is e to the power minus lambda r upon r square, not only on r square, now let us understand that if there is some kind of difference, if I create and I say that now my field, instead of having an inverse square law dependence, now force or the field varies as if it is e to the power minus lambda r upon r square. Now you can see that if I have this charge q centered here, and if it follows this kind of dependence, I'm very sure that instead of kq upon r square, there will be some field, there will be some, like I would write this as a constant. Let's say if I want to write net electric field, let us write kq and all those things as capital K, which is a constant here. And then you have e to the power minus lambda r upon r square. So just for conveniences, I've written this as a constant. Forget about it. Overall, understand that if your electric field has this sort of dependence, that is e to the power minus lambda r upon r square, then does your Gauss law still be valid in the original form? So question is, the Gauss law in the present form, is it still valid? The Gauss law in present form, is it still valid? This is a question that I'm going to raise. For example, if I have this charge Q, and if I want to say what is the net flux enclosed, so let us draw a radius. Let us draw a sphere of radius, let's say capital R. Okay. Now, what is the flux enclosed through this? So, what is the flux linked through this surface? The flux linked through this surface will be E dot ds integral over this surface, let's say S, and this will be equals to integral. Forget about this constant, I'm writing it outside. So, this will be minus e to the power minus lambda upon r square. And then you have r square sine theta d phi. Okay. And if you integrate this stuff up, you will get what? You will get, I think, 4 pi k. Keep it as a constant. Forget about it. I'm not much concerned. And now your flux enclosed depends upon the radius of the Gaussian surface. It depends upon the radius of the Gaussian surface. As you can see here, there is a dependence over r. What does it imply? It implies that if I take r tends to infinite, if I take r tends to infinite, what I expect from my original Gauss law, even if I make as large a surface, even if I make this surface as large as possible, in the present form, in the form that I know that total charge enclosed is q upon epsilon. So if I go with something like, if I had 1 upon r square kind of variation, I knew that my flux in any case would be a constant value and should be equal to q upon epsilon naught, even if r tends to infinite. But here I'm seeing that as r tends to infinite, this flux enclosed is going towards 0 rather than being constant, constant. Is that clear to you? So overall, understand that obviously the Gauss law would be there is some modification to Gauss law that would be required for certain such cases. But overall, understand if whatever Gauss law that we are writing, E dot ds is equal to integral E dot ds equal to summation q upon epsilon, understand that this particular Gaussian expression, or you can say this particular Gaussian law, is valid only for inverse squared law forces. Only then you can write the net flux enclosed is given by some constant. That constant is whatever charge enclosed within that Gaussian surface divided by epsilon. But if you take certain different sort of expression, let's say this is a kind of expression which is, you can say, a screen Coulomb potential that I've already talked about, or probably a Yukavian kind of field. here you would find that if I just try to imitate and just try to find my flux happens to be a radial dependent flux. It implies what? For finite radiuses, for finite radii, what will happen? For finite radii, there would be some field apart from this field from the point charge on the sphere surface also, apart from the field created by this point charge. So apart from the field created by point charge, there would be some field, because there is some flux extra enclosed. This is like e to the power minus lambda. So again, there is some excess of flux that is enclosed apart from this Q. Is that clear to you? Okay. Overall, understand that even as R tends to infinite, if our original Gauss law is still to be valid, then what happens is, let's say, even if I take large surfaces also, I understand that total charge enclosed should anyway remain Q over epsilon. But if in case, if I use this kind of definition, instead of inverse square law, if I use e to the power minus lambda upon R square, I'm amazed to find that this Gauss law, this net flux enclosed is dependent over e to the power, like it is dependent on R. So what does it imply? If you take R tends to infinity, your net flux enclosed would be 0. However, you can see that even if I take R very large, my net charge enclosed is Q. So obviously this kind of thing cannot be valid. So I will have to certainly modify my Gauss law in order to obtain. So that is what I want to say, that for such cases we'll have to modify our Gauss law. But overall, understand that this kind of Gauss law is only valid for inverse square law. So there are questions. It has been asked in JEE examination for like students also, for 11th and 12th, and many a times people ask this kind of question: whatever you're writing, this sort of Gauss law, is it valid for some other kind of expression? The answer is no. For example, I will discuss all these things quite in detail also, but just giving you an insight. For example, if your electric field was dependent upon 1 upon r to the power 2 plus del, if this kind of dependence was there, then also you can see that your net flux enclosed through a surface S would be given by, let's say, this particular surface S, for simplicity, is your spherical surface, so that calculations remain easy for me. So if it is like this way, so total flux enclosed or total flux linked with this particular surface S is given by K Q upon R to the power del, and there should be a 4 pi here. So you can understand that again my net flux enclosed is dependent upon the, so flux enclosed, your flux linked is dependent upon the choice of the Gaussian surfaces, dependent on the choice of the Gaussian surface. So for example, if I take this Gaussian surface to be a different sort of thing, again, if I take it in a manner that it is having a very large radius, then things would change. Small radius, things would change. But however, I know that my net charge enclosed is Q only. So it cannot be the case. So for example, if I want to write that my flux should be equal to net charge enclosed divided by epsilon naught, it implies that I will have to certainly modify my definition. And so there I'm heading to the first of the cases. I hope it is clear till now. Is that clear? कि नहीं समझ में आ रहा? Please let me know.
Yes, sir. Clear.
Clear. Good. So, for example, if I just take an example, and this example is again from, I think, Griffith only. Just take this example, and you'll understand what I want to suggest. And if you just people do at least standard 12 things on your own, then we'll at least head to some more serious things. For example, if your Coulomb's law, is sort of modified in this present form. Now, your Coulomb's law is given by F vector is equals to 1 upon 4 pi epsilon naught, and this is Q1 Q2 upon R square, and then you have this 1 plus R upon lambda, and then you have e to the power minus R upon lambda, and then you have this R cap. So if your Coulomb's law is modified to this definition, what do you think would be impacted? So first thing that I want to ask is, do you really think that your definition to field would be impacted? Answer is no, because field is ultimately like impacted what? I mean, you can actually derive your field also. That is not at all an issue. So you can derive your field, and now you can write your field as, instead of k q1 q2 upon r square, you can write your field as 1 upon 4 pi epsilon naught. Let's say your point charge q is there, and so forth. For that point charge q, you can write your this expression. So this is your field. Is that clear? And if you want to write for a generalized volume distribution, if you want to write it for a generalized volume distribution, so for example, then your q can be written as integral rho theta. So there you can write this electric field as a function of r vector as 1 upon 4 pi epsilon naught. And you can write q, instead of q, you can write integration rho. And here you can have r dash for all these things. I'm not writing that up. So you can write rho upon r square, and this is 1 plus r upon lambda e to the power minus r upon lambda. And then you can have theta. So in this manner also you can write. Okay. So overall, understand that electric field as such would not vary. Electric field would as such depends on force only. That is absolutely fine. But the question that arises is whether this sort of field, this field, admit a scalar potential. Admit a scalar potential. Now here I want to draw your attention to something called as conservative forces. So what do you mean by conservative forces? Just giving you an idea. Okay, or conservative fields. So mathematically, if I want to say that my field F vector or E vector is a conservative vector field, so what does math say? Math says that if you are saying that your field is conservative, so math says these kind of fields are irrotational. And what do I mean by irrotational? That if you want to take the curl, that turns out to be zero. That turns out to be zero. So if you take the curl of F vector, then it comes out to be zero. It comes out to be null vector. So for example, your electric field, which derives from static point charges, so electric field, which we derive in electrostatic conditions that I want to suggest, is a conservative vector field. It is a conservative vector field. And conservative vector field means what? So if, for example, there is a definition, there is a theorem in vector calculus which says curl of a gradient is always zero. Is always zero. So curl of a gradient is always zero. So what does it suggest? It suggests me that my f vector can be written as gradient of some function, and that particular function is called as scalar function. Scalar potential function. That scalar field function is called as a potential function. So whenever you are dealing with the conservative fields, the first thing that comes up in mind is that the curl of that particular field should be zero. Secondly, that particular field can be written as minus gradient of some phi. You may be thinking why minus, because this is in consistency with the direction. So don't get confused. But overall, you can write it in a way that it can be written as gradient of some function, and that is, so obviously understand any conservative vector field would always admit a scalar potential. The other two properties regarding this is, for example, if I want to find the work done in moving a charged particle here, because we are talking about electrostatic forces from R1 to R2. So if I want to move my charged particle from R1 to R2, my net work done is given by F dot dr vector. Okay, and if I want move from R1 to R2, this will be your net work done. And eventually, I know that my F can be written as minus of grad of phi dot dr from R1 to R2. And this is minus del phi upon del r r cap. So overall, you will understand that this is nothing but it is equals to f of r2 minus f of phi of r2 minus phi of r1. Because this grad phi is what? It is like del phi upon del r r cap. So r cap dot r cap gets 1, del phi upon del r cancels. So del phi by integrated from r1 to r2 will give you phi r2 minus phi r1. So what do you get? You get that work done in moving a particle, or work done by this particular force, which is a conservative force, is always independent of part taken. Rather, it depends upon initial and final points, independent of the part taken. So basically what happens, this particular integral only depends upon final and initial position. It does not depend whether you go this way, whether you go this way, whether you come from anywhere. But ultimately, if your initial and final points are R1 and R2, as long as this is fine, then total work done will remain the same, irrespective of what path you choose. So all these properties I'm writing are same way of writing conservative vector forces. So for example, a standard 12th child would say that, okay, work done, because standard 11th child has some sort of insight about work energy power. So he may say that a conservative vector field is one where the work done by that particular field, let's say moving a point mass or charge or whatsoever the condition demands me, that particular work done is independent of the part taken and only depends on final and initial position. A person who has some insight in vector calculus would suggest that conservative vector fields are those vector fields whose curl is zero, or in other words, they're irrotational vectors. And also, this particular idea would certainly generate another idea that if a field is a conservative vector field, then vector field can be written as gradient of some scalar function that is a potential function. So overall, all these are conditioned. And fourth property at times people refer to as, they say that work done along the closed path is always zero. So work done along the closed path is always zero. So that part also we know. So that we know, if your path is closed, then R1 is equal to R2, then your work done along a closed path comes out to be zero. So all these things are the same way of writing your conservative vector field. The fifth way can be also to write that for conservative vector fields, these are not kind of dissipative fields. You can say that a total energy, that total mechanical energy remains constant. So it depends upon which school of thought you are. For example, if you really believe in your energy things, so you will say that, okay, the total mechanical energy of the system remains constant. Remains constant or remains conserved. So these are the same ways of writing. I'm just giving you an idea. I'm not very much rigorously writing all these things, but overall understand that all these things are quite necessary things. Or you can see these are the attributes of your conservative vector field. So this is the question that I'm now arising all over again. That you see your field force to be defined as 1 upon 4 pi epsilon naught q1 q2 upon r square 1 plus r upon lambda e to the power minus r by lambda, and a certain observation that you see from here, that if your lambda tends towards infinity, you can clearly see that this particular force would actually behave as if it is a Coulombian force. You can see that this will be like k q1 q2 on r square. You just take lambda tends to infinity, this would go 0, this would go 0, e raised to power 0 is 1, and this is 0. So overall, you understand your total force is given by 1 upon 4 pi epsilon naught q1 q2 upon r square r cap. So this is certain modification, probably because of experimentation or anything, may give such kind of forces. The question arises whether it will admit a scalar potential or not. This question is still there. Just let me know whether it will admit a scalar potential or not. So again, I will draw your attention to something called as central forces. So I hope people might have taken some lectures on central forces. We have not started it yet, but we know that central forces are conservative forces. This is something that we know. Okay. Even if you don't know, you just take one example. For example, you just take that your force in general is dependent on k r ki power. Let's say this is your force, because you know that central forces are only radius dependent forces. You just take this k r ki power, and then you just try to find, this is something that I'm giving you as a homework. You just try to find this curl, and you immediately find that this will be 0. So curl of this vector field, the curl of this particular force, which is given by k r ki power n, will be 0. Will be 0. This is what I'm trying to tell. So in any case, such forces are conservative forces. Always understand that your central forces are conservative forces. If they are conservative forces, then you understand another, or you can say you just take any function of r. You just take any function of r. You take f to be any function of r. So if you take from f to be any function of r, then also your force is a conservative force. So for example, the above force that you see is also a conservative force, isn't it? You can just see in this entire expression, you have only force depending upon r. So this is a conservative force. So this is a central force, and central force means, again, it is a conservative force. Is that clear to you or not clear to you? मैं थोड़ा तेज बोल रहा हूँ क्या?
Sir, clear.
Clear. ठीक है. वाजा है, भरत आया.
हाँ जी सर, क्लियर सर.
यार कल वाला ही वापस हो रहा है ना, पर कोई बात नहीं. एक दिन वो कल एक्चुअली
नहीं कोई बात सर, अच्छा है.
चलेगा ना? ठीक है. So understand that this curl of this central field is always 0. Okay, and you can see that if I just remember the formula correctly, let me just give that formula so that you can self-verify it your own self. So for example, if I want to find the curl, because here you have this radial dependence. So what you can do, del cross F vector, if you even take this kind of force, or even if you take this kind of force, so what will be it? I think if I remember correctly, this will be r theta cap, and this will be r sine theta. I mean, I will take certain lecture for vector calculus also, but this is what I want to suggest कि थोड़ा सा you start doing on your own self also. तो क्या होगा, चीजें आसान हो जाएंगी क्योंकि बहुत बेसिक्स भी कराऊंगा, then you will get कि यार इसमें कुछ नया नहीं समझ में आ रहा. So for example, you know here, so for example, here you have this radial component of force which happens to be Fr here. So I'll write Fr here. You know that there is no theta component of force, so I'll write 0, and you know that there is no phi component of force, so you'll write 0. Now here you can clearly see, if you want to find this curl, you will ultimately get this answer as 0. So overall, understand that whether you write f of r or whether you write k r ki power n, this particular you just find this determinant and you will find that this is 0. Is that clear to you? Just take this determinant. I know this is quite easy for you. You do it on your own self. Understand this is not a function of theta and phi, it is only function of r. So understand that this particular force, which I have written all above, it entirely depends on r. Since it entirely depends on r, so it is a central force. And if it is a central force, then understand that this is a conservative force also. And you can see that otherwise also, if I just encapsulate this entire thing by writing that this is some function of our fr, then I know that del cross f would be 0. It implies that the above written modified Coulomb's law, would definitely admit a scalar potential. Scalar potential. Now question arises, will it really you can say that what should I say? What should we like? What do you think about Gauss law? What do you think about the Gauss law? For example, if I want to write that, will E dot ds to surface S is equals to Q upon epsilon naught, will that be the case here? That is, Gauss law be valid in the form that we know. So will Gauss law be still valid in the form that we know? This is one thing that we are going to address in this particular discussion. Overall, understand all other properties would remain the same. Like for example, if you say, will the energy be conserved? Yes, energy will be conserved. Why energy would be conserved? Because this is again a central force. If you have a central force, then Gauss law, if it is a central force, then it is a conservative force, and conservative force means all those 5 properties I listed above would still be valid. But only point is, will it admit a scalar potential? Yes, it will admit a scalar potential that I've already done, because del cross f is 0. That implies your f vector can be written as some minus grad of some phi. And this ultimately leads me to find what will be the potential. What would be the potential at an arbitrary point r? So you know that whenever you have to find a potential, what you do? You try to integrate your electric field, the line integral of electric field from r reference to the point, let's say r. If you don't get confused, if you get confused, then you can place r dash here. If you don't get confused, then it is fine. Okay, so overall understand how to find the potential at a point r. You can simply take this line integral, that is E dot dr, from r reference to r, and this r reference is such a point where your potential happens to be 0. So happens to be 0. So conveniently, we can here take r tends to infinity as a reference point. R tends to infinity as a reference point. Is that clear? So if I take my r reference as an infinite point, so this will give you E dot dr. This will be your potential. So potential as a function of r would be minus integral from infinity to. अच्छा, एक और चीज समझने की कोशिश करो. If your field is radially outwards, which indeed is the case, which we can see here. Here is the case. See, you can see all these things are positive, isn't it? All these things are positive. Q1, Q2, r square, 1 plus r upon lambda. All these things are positive. If you understand that if all these things are positive, you can see that your field is radially outwards. And if I try to bring my charge particle from infinite to this particular point, I'm moving opposite. Okay, is that clear? So I'm moving opposite. So this is the direction of my electric field. This is the direction of my approach. Always understand, ये चीज बहुत गलत करते हैं बच्चे, इसलिए बोल रहा हूँ. Always understand that dr always is in the increasing direction of r. So dr vector is always in the increasing direction of r. कैसे? For example, this is your x, and now you move to x plus dx. So if you take this difference, this will come out as dx, and this is positive only if it is positive only then it will come from here to here. Now, if you want to come from here to here, so for example, if you are here and if you want to come here, what does it imply? It implies that you are now moving towards the origin. If you move towards the origin, if you move towards the origin, now your dx would be negative, because now if you increment, if you only decrement, only then you can move towards the origin. If you are incrementing from the origin, then you are going away from the origin. And if you are decreasing, I mean, if it is in the decreasing direction of r. So in general, understand, if I write dr vector mod, what does it imply? Dr vector mod implies you have to write the positive of this. So if dr is positive, then I will simply write it as dr. You just forget about this r mod. So if your dr is positive, I'll write dr. And if your dr is negative, I will write minus dr. So always understand, if you're moving towards the origin, since your dr would be negative, only if it is negative, only then you can move in this direction. Huh? In that case, your dr mod would be minus dr. I mean, I have several times seen my standard 12 student doing wrong here. या तो उनको स्कूल में कोई कुछ गलत बताता है, पता नहीं वो क्या करते हैं. So you just follow the definition जो तुम्हें आती है. You just try to follow this, what I'm saying. So this will be E vector mod. This will be my dr vector mod. And understand what is the angle between the two. Electric field is outward and you are coming inward. So this will be cos of pi. Is that clear? Okay, so this cos of pi, and this will be plus infinity to r. Electric field ka mod is E. What is dr ka mod? Dr ka mod is dr. But understand where I'm heading to. I'm heading towards the origin. It implies my dr should be negative. But again, modulus means what? You have to write positive things. So if instead inside cheese jo likhi hui hai, if inside you have a negative thing, then what do you impose? You impose a negative again in front of it in order to make it a positive. So ultimately, this happens to be the case. Okay, so there are two nullifications of negatives. One from cos pi and another from this dr1. This usually people forget, and then there is a sign discrepancy in the answer. Don't forget this. Is that clear to you?
Yes, sir. Nice, sir.
Anna, try to write this. And if you want to write r dash also, it's fine. If you don't want to write r dash and it's clear to you, then I'm not going to place all those things. So it is 1/4 pi epsilon naught. And then you have q. And I think you have this r square. And then you have 1 plus r upon lambda. And you have e to the power minus r upon lambda and this dr. Okay, let us try to find this integration. This integration would give you v as a function of r. What I would do is I would try to integrate by parts. If I try to integrate by parts, or I will simply take this negative one out. So 1/4 pi epsilon naught would lie from r to infinite, and this q upon r square, and then you have 1 plus r upon lambda, and then you have e to the power minus r upon lambda dr. And now you just try to take this integral of this, I guess. I think this will be integrated. Overall, I think you'll be able to find this integration. Just try to find this integration. We have some time. If you can find it fastly, तो अच्छा रहेगा. इसी लेक्चर में खत्म हो जाएगा, नहीं तो अगला लेक्चर भी इसी पे देना पड़ेगा. चलो देखते. So if I integrate this entire stuff, this will be, I think, q upon r square 1 plus r upon lambda. Integral of this will be e to the power minus r upon lambda upon minus 1 upon lambda, right? So this will be minus lambda, again minus integral, the derivative part of this. So derivative of this would be, I mean, समझ में तो आ रहा है ना ये सब, कुछ कचरा तो नहीं हो रहा. Find the derivative of this and find integral. I just want you to find this integral for me, because there is lack of time and then there is lack of space also. I'll meet you in the next lecture, but meantime, you just try to figure out what this integral would be. I'm giving you just 2 minutes or so. There are only 2 minutes remaining in the lecture, so kindly find this integral, and I also find it subsequently. Just try to find it, this integral.